When enabling OSPF on a Cisco router, it's a two-step process. Number one, we have to enable the router process, which we've taken a look at in a previous video, but we also need to tell that router which networks that it's directly connected to, which networks we want to include as part of OSPF. And it's that part of the configuration that I'd like to chat with you about in this video. So on R1, if we want to enable OSPF, the routing process, we'd go into configuration mode and type the command router space OSPF space, and then our process ID. And our example used in the previous video is a process ID of 1, and then press return. And boom, we have OSPF running, and it has at that moment also chosen a router ID based on the pecking order that we also discussed in a previous video. Now, the next challenge, once OSPF is running, is which networks do we want to include in that routing process? And that is done with a special command called network space. And then following that network statement, we're going to train the router on which directly connected networks we want to include in OSPF. Now, I have to admit, it's a bit interesting on how it's done, because the network statement does a couple of things. The network statement says what we're going to match on. That's the first step of this network statement. And then secondly, based on the interfaces where the IP addresses match this network statement, we're going to go ahead and include those directly connected networks. And so let's take a look at R1. R1 has, in this example, 3 interfaces, gig 00, 10, and 20. And it has IP addresses configured on each of those respective interfaces of 10.1.0 with .1 in that last octet for each of them, 10.12.0.1, and also 10.13.0.1. And each of these networks has a 24-bit mask. So it's the 10.1.0 network, 10.12.0 network, and the 10.13.0 network that R1 is directly connected to. So for our network statement, what we're going to do is we are going to put in the first step here. What do we want the router to match on? Let's imagine that we want the router to match on the exact IP address of 10.1.0.1. And we could say that, okay, dear Mr. Router, if you have any interfaces that have this exact 32 bits, we want to include those directly connected networks, in this case, the 10.1.0 network, as part of OSPF. It's match, and then include those directly connected networks. Now, the second half of this statement, network 10.1.0.1, we also need to specify how many of those bits do we want to have the router match on. And you might say, well, Keith, we just said we want to match on the whole thing, 32 bits. Well, in that case, if we want to match on the whole 32 bits, we would use a wildcard mask that says we care about all of it. And here's what that wildcard mask would say. It would say 0, which means I care about matching on the first octet. 0, I care about matching on the second octet. 0, I care about matching on the third octet. And the last 0 is it cares about matching on the fourth octet. And then we'd follow up with a space, and then area, space, and then the area that we want any matching networks to go into. And so in our topology, we're going to use area 0 across the board. So let's think through this together as if you and I are router 1. We would look at this network statement saying, okay, do I have any interfaces that exactly match these 32 bits, 10.1.0.1? So it does a quick check. Yes, I do. And as a result, I need to put that directly connected network on gig 00, the 10.1.0 network, include that as part of OSPF. Now, the challenge with this is that if we had 15 interfaces, we'd have to have 15 network statements, just like this, with the appropriate IP address to have that router add all the interfaces. So another way of doing this is to use a network statement under OSPF that could include multiple interfaces at the same time. What do you mean, Keith? Well, check this out. We have every interface here starts with 10. So what we could do is we could say network 10 dot, and then for these 3 characters or 3 octets, I'm going to put X's just as placeholders for a moment, space, and then with the wildcard mask, we could say we care about matching the first octet, hence this 0 says I care about matching, but for these last 3 octets, we could say 255, which represents 8 bits, 8 wild bits, meaning I don't care what's in those 8 bits of that second octet, and 255 mapping up to the third octet, saying I don't care what's in those bits either, and then 255. So these are called wildcard bits because they tell the router, doesn't matter, not looking at those, don't compare those. In this case, the router would look for any interfaces that begin with 10 anything, and then it would put those directly connected networks into that OSPF process. And we'd also want to include a space, an area, and then specify the area number. So in our topology, we're putting all of our routes, all of our networks into area 0. So let's do a couple more to make sure we get the gist, the kind of idea of how this works. And let's use a network statement again. And this, in fact, let's pretend that this network statement doesn't exist, this network statement doesn't exist, and we're using the network statement of 10.12.0.0 with a wildcard mask of 0.0.255.255, and we'll put any directly connected networks that match that into area 0. Okay, so if this was the only network statement we had in OSPF, my question for you is which of these networks, if any, would be included inside of OSPF based on this single network statement that we just put in right here. And let's compare notes. So with this network statement, the first step is matching. The router is going to take a look and say, okay, what matches here? And based on the network statement of 10.12.0.0 with a wildcard mask saying, I don't care what those last 2 octets are. They could be any bits on, any bits off. I just don't care, says the wildcard mask. I just care about matching on the first 2 octets, the 10 and the 12. So if we look at the interfaces here, the only interface that has those first 2 octets of 10.12 is gig 1/0. So gig 1/0 would be the winner, and then gig 1/0, that directly connected network of 10.12.0, the network that's there on that interface, would be included as part of OSPF. And we're going to have many opportunities in this skill to practice and reinforce using wildcard masks. And let me give you one more example. Let's cross that one off. And let's do something like this. Network. And then the wildcard mask of all 255s, meaning all bits on in the wildcard mask. And then we'll follow it by adding any matching networks into area 0. All right, so now, with just this one network statement, if that's all we had in the router process, which of these networks, if any, would be included as part of the OSPF routing process? And if you're looking at the wildcard mask and saying, well, the wildcard mask says, I don't care, I don't care, I don't care, I don't care, you'd be right. This wildcard mask, because it says I don't care what the values are, would cause every directly connected network to match. So in this video, we've introduced the idea of a network statement, including the concept of a wildcard mask. And also, in the future, if we're talking to a friend and they're talking about something that we just don't care about, we can say, 255, dude, 255. Because the wildcard mask, if those bits are on in that wildcard mask, it means we don't care about matching on any of the corresponding bits that are part of the network statement, based on the wildcard mask saying, I just don't care what those values are. So we'll have plenty of opportunity to practice and reinforce working with wildcard masks as we implement network statements. And we're going to do that starting in the very next video. So I'll see you there in just a moment. Meanwhile, I hope this has been informative for you. And I'd like to thank you for viewing.